don't think I'm tracking what you're saying, to be honest.
Okay, no worries.
Um, yeah, there can be things that are problematic about presuppositionalism, if that's just what you're getting at.
We all have presuppositions. We all need to work on to do anything. Math is a literal category of
Mhm.
just presuppositions and axioms that we take into account to do like logarithmic work. Sorry,
Yeah.
to do any kind of arithmetic. Um,
Mhm.
I'm sitting here and just telling you, what's the point in having your specific presuppositions if they're useless?
Yeah, if there are useless presuppositions, sure, they're not useful to have. I agree. But I think there's lots of useful presuppositions, of course, yeah.
Yeah,
Mhm.
like universalism. Sorry, not universalism. Uniformitarianism. There we go.
Or like trigonometry, you know, like
That is a class of
trigonometries.
mathematics that we do hold, yeah.
Yeah.
Mm.
Yeah, it we love to think that that's true, and it's incredibly useful to the real world. I mean, until it isn't, but you know.
I find there's not often many instances where like assuming like say typically granted facts in geometry, like typical presuppositions where that's not useful. I think most of the time it is.
Um, I mean, I'm not sure what you mean
Like
by
for
that.
example, in physics, like we
Uh-huh.
use geometry all the time, and we use our presuppositions about geometry to make really accurate claims about the world.
Sure, technically we're using approximations to the abstract made up concept of geometry. We don't actually think that actual triangles exist or actual circles exist.
Yeah, of
In
course. Of
fact,
course.
we're probably certain that those are impossible, right? Um, so the math is useful, right? But it's even
Is that
more.
true for all shapes though? Like I get it for
Uh huh.
like circles,
Uh huh.
but like
Well, any.
there's other shapes that are like a circle is very obviously difficult to make in any like physical realm.
Uh huh.
But that's not true for like all unless like you're being really stringent on the definition and saying like it has to be part of like a 2D plane to be like a triangle, say.
No.
But you can have like, you know, the hypotenuse adjacent and what's the other one? Um,
Opposite.
Opposite, yeah. You can have like those components
Mm-hmm.
of a shape and you can have them all add up to 180 degrees when you measure them.
Yeah, assuming that the sides are straight and all that, right? But yeah. But again,
Yeah,
the
but I
real
feel like that's much more plausible, obviously, than like a circle, you know?
well, the real world um, is using approximations to those things, right?
Yeah, like they're imperfect versions, yeah.
Yeah. Um, yeah, but certainly it's worse than that, though, right? Like that's just a very easy way to understand the difference between abstraction and reality. In mathematics, it clearly gets much worse. Like, we don't even know if arithmetic is consistent. That's the first theorem of Gödel's incompleteness theorem. So, like, if you were to say something, like, oh, well, we know with 100% certainty that 2 plus 2 equals 4, well, technically, no. We don't know that 2 plus 2 equals 4 is only true. It could also be true and false because we don't know that arithmetic is consistent. It is certainly the case that 2 plus 2 equals 4 follows from any number of the axioms that have been developed, like Peano axioms, right? But it's not the case that those same axioms demonstrate that 2 plus 2 doesn't equal 4 is not a theorem, right? That could also be a theorem, meaning that the system is inconsistent, right?
I need to look into Gödel's incompleteness theorem because I don't
Mm-hmm.
really know much about it. Like I know somewhat what it's about, but I don't really understand it, I don't think.
Well, it's broken into two parts, and the first part is that any system capable of expressing arithmetic cannot be proven to be consistent. So you don't know if the axioms form a contradiction or not. Um,
Virtue of what?
what do you mean, virtue of what?
Like why? How do you know that's true?
Oh, how did Gödel prove it? That's a much more
Yeah.
complicated question. He did it in a higher order logic, obviously, because how would you analyze a lower order logic without a higher order logic? And he did it through a very
Right.
complicated process called Gödel numbering, right? Um, Effectively, what he demonstrated was that the very act of trying to develop a logic system meant that you were making certain assumptions about how arithmetic would behave in the first place. And he was able to use that biased assumption in the meta logic and put it in one-to-one correspondence with the defined arithmetic within the lower logic. This inevitably had like a feedback problem, and he was able to therefore demonstrate that it is not possible to show that the arithmetic that we thought we had created in a very clean box separate from the real world is actually not separate from the real world. That the very act of trying to create arithmetic itself assumed arithmetic, right? And therefore he was able to demonstrate in a very logical way, right, that arithmetic is you cannot show arithmetic is inconsistent, right? And so that will always be unknown to us. It is not possible for us to come up with a proof that demonstrates that arithmetic is in fact consistent. It could always be the case that any axioms that we come up with for arithmetic could always contain a contradiction in them, and we'll just always be in the unknown on that, right? Um,
Right.
the second part of Gödel's incompleteness theorem, which many take as far worse than the first one, right? Gödel demonstrated that even if you assume arithmetic is consistent, so you just assume it, there will always be statements that are true that you can never prove are true. So that's the second part, is that even if you assumed it was consistent, there will always be true things that can never be proven to be true about arithmetic. So statements about arithmetic that are true and that cannot be proven to be true, right?
It's interesting.
And so arithmetic will always be, as we call it, incomplete.
Mm, that's interesting.
Yeah, it's very interesting.
I just find it very difficult to like I can understand the reasoning. I just find it very difficult to like conceptualize
Hmm.
um
Well, yeah,
that in any meaningful sense, if that makes sense.
well, sure, but and the reason, but this is why theists typically are in the wrong here when they try to do abstract reasoning and they say dumbass shit like, well, 1 + 1 = 2 is a guaranteed truth, and I'd have to be like, in what sense? Because in the real world sense, 1 + 1 = 2 is true because of the evidence associated to what those words mean and how we use them and the examples that we've, generated around them. But in the abstract world, you don't even get the luxury of being able to say that it's true in the abstract world. Not in any not in any guaranteed sense, not in any 100% sense, because either it's a theorem that was developed from a set of axioms that you can't even demonstrate are not inconsistent, or you can assume that they're not inconsistent and you still arrive at the fact that the entire arithmetic system is incomplete. Meaning that, yes, 1 + 1
Uh-huh.
= 2, but that doesn't mean that you'll be able to know everything about arithmetic. There will always be other statements about arithmetic that can never be proven to be true. And yeah, those both are incredibly unintuitive, but they fly right in the face of theists that try to talk about these absolutisms or whatnot, because that's just all made up bullshit, right?
Hmm.